Hi, we are from Group 16. So today we would like to do a video presentation for designing an experiment. So this is our group member. Hi, my name is Nora and my number is Arzali. Matrix number 17181914. Today I would like to start presentation with an introduction. What is the 3D dynamics of rigid bodies? 3D dynamics of rigid bodies. Motion has three component of vectors representing force, linear velocity, and also linear momentum. It also has two additional components for vectors representing angular quantities, which are moments of forces, angular velocity, angular acceleration, and also angular momentum. There are several possible motions of 3D kinematics of rigid bodies, including rotation about a fixed point. For example of the motion is fan blade motion. Okay, next we have 4-bar mechanism. 4-bar mechanism consists of 4 bars connected by the pins, which allow them to move freely. The first bar is fixed bar, where it fixed in place so that it cannot move. Second, we have crank. Crank is a bar that connected to a motor that causes fan to move around. And third and fourth, we have coupler and follower bar that force to move to follow the motion. As you can see from the picture, the mechanism has different lengths of the bar that can cause a swivel motion for the fan. By understanding the 3D rigid body motions and also 4-bar mechanism, we have designed an experiment to estimate the speed of the fan blade rotating about its axis, to calculate velocity and acceleration of the tip of the fan blade at the lowest and highest speed setting, and also to estimate the speed of the swivel of the fan.
Import the video into Kinovia software. Set the beginning until the ending of the clip. Select track path and add a few numbers of frames until it completes one revolution. Select a line and draw a line. And calibrate it into 5 centimeters. Draw a line to measure the length of the middle of the motor to the center of the fan blade. Select the first frames and add the stopwatch. Configure the stopwatch and label it. Start the stopwatch. Observe the swivel of the fan until it completes the motion. Select the track path and configure the measurement into speed. Now we can see the motion of one complete revolution labeled as meter per second. Then repeat the same procedure for the highest speed. For swivel of fan, the length from the center of the motor to the fan blade, which is O to C, is 14.5 centimeters. Both tables shows the collected speed, which is the slowest and the highest. For the average speed for the slowest is 0.022 meter per second, while the average speed for the highest is 0.029 meter per second. After obtaining the linear velocity, we need to convert it into angular velocity by using the formula V equal omega times R. The angular velocity for the slowest speed is 0.1517 rad per second, while for the highest speed would be 0.2 rad per second.
Hi, I'm GUI7, metric number KIB 190017. Next, I'll be presenting for the calculation part. During the lower speed of the fan, which is fan speed 1, the speed of the fan blade rotating about its axis, omega naught equals to 30.1946 radian per second, which is at z-axis here. And the fan swivel at a constant speed, which is represented by capital omega equals to 0.1517 radian per second, which is at capital Z-axis here. And the position of the tip of the fan blade is located 18.5 cm from the Z-axis, which is distant from point A to point C, while 14.5 cm is the distance from point O to point C. Thus, it is represented by vector R equals to 0.185J plus 0.145K in meter unit. The direction of Z-axis is represented by vector k equals to j cos theta plus k sin theta. We assume that the arm of the fan is raised at the position of theta equals to 10 degrees. In this experiment, we need to calculate the velocity and acceleration of the tip of the fan blade. So, to obtain the value of velocity and acceleration of the tip of the fan blade, we need to calculate the angular velocity and angular acceleration of the tip of the fan blade first. The angular velocity of the tip of the fan blade, omega, is equals to omega naught plus capital omega. Just now we have found that the value of omega naught is equals to 30.1946 radian per second multiplied with k, which is in z-axis direction. And the value of capital omega is equals to 0.1517 radian per second. And it needs to be multiplied with the vector k, which is cos tan theta j plus sin tan theta k, to resolve it into perpendicular components in z-axis and y-axis direction. Then we will get the answer of 0.1494j plus 30.2209 k radian per second. Next, we will calculate the angular acceleration of the tip of the fan blade. Angular acceleration, also known as the derivative of angular velocity, is equal to capital omega cross product with the omega that we found before. So the final answer will be equals to 4.511 I radian per second square. Now we are able to calculate for the velocity of the tip of the fan blade. We know that the formula is V equals to R omega. However, in this situation, since it is in vector, so we need to use V equals to omega cross product with R. R is the position of the tip of the fan blade just now. So we will get the final answer, which is negative 5.5692 I meter per second. Finally, we calculate the acceleration of the tip of the fan blade. The acceleration is equal to angular acceleration, which is the derivative of the angular velocity cross product with the position of the tip of the fan blade plus the omega cross product with the velocity. At here, omega cross product with R is the velocity of the tip of the fan blade we have calculated just now. Finally, we will get the answer for the acceleration of the tip of the fan blade equals to negative 168.9602 J plus 1.6665 K meter per second squared.
Hello, my name is Untitled Chapter, KIB 19003. So, moving on to my part, which is the calculation of the fastest speed of fan, which is 3. So the fan blade rotating at its axis at a constant speed is omega naught 48.5135 rad per second. The fan swivel at constant speed is omega equals to 0.2 rad per second. So the position of the tip of the fan blade and the direction of z-axis, which is r and k respectively, will not be changed for this calculation because we have the same parameters except for the speed. And we assume that the arm of the fan is raised at a position of 10 degrees. Knowing all that parameters, we can now calculate the velocity and the acceleration of the tip of the fan blade. Before we calculate both of those, we have to calculate the angular velocity and the acceleration to get the velocity and acceleration of the tip. So, omega is omega naught to be added with omega multiplied with k, which is the z-axis and the y-axis. With that, we get 0.1970 J plus 48.5482 rad per second. For angular acceleration, angular acceleration can be also called omega with the dot, and it's equals to omega times the k, which is the direction, times with the omega. And we use the cross product rule, cross product formula, which is cross one out and multiply, cross one out, multiply, cross one out and multiply, and we get 9.555 r rad per second square. So with all that information, we can now calculate the velocity and the acceleration. For velocity is omega times r, which is the position of the tip of the fan of the blade, because we know that from C to A is 0.185 and O to C is 0.145. And we use the cross product rule to get negative 8.9529 I meter per second. And next we have the acceleration, which is the omega dot times r plus omega times the v, which is omega times r. So both are cross product too, and we use the same formula to get negative 436.0327 J plus 3.5314 K meter per second square. Thank you.
In conclusion, as we can see before this, the calculation part, we can conclude that when the speed of the fan is increasing, the velocity and acceleration of the tip of the fan blade are also increasing. There are also some errors and precautions that need to be taken into account in this experiment. First of all, inconsistent reading of linear velocity and also linear acceleration. Second, a distinct and clearer marker is suggested to be used in this experiment. Third, use at least 60 fps to capture the motions of the fan, because it is more likely to capture twice as much underlying data. Okay, that's all from our group. Thank you.